Hi, my name's Andre. Thank you for clicking on my video. I think you're one of the first. I'm going to show you how to derive a formula for the speed of a falling object, including air resistance. You know, you always get these problems in textbooks and they ask you to solve these motion problems but neglect air resistance. So I don't want to do that. I'm going to include it. And I'll calculate this air resistance by using the drag formula. There are lots of videos on YouTube that can make you familiar with the drag formula. The force of gravity will be held constant in the problem, so I will not be taking into account the reciprocal squared nature of it. The force diagram only has two forces acting on the object. Gravity, of course, is down, and drag necessarily opposes motion. So since we're falling down, the drag will be up. I used positive down because as you fall, you speed up, so the velocity is increasing. It's just the way I was going to do it. So we're going to start by finding an equation for terminal velocity. Now, terminal velocity is a constant, so the acceleration is 0. So I'm saying at terminal velocity, the sum of forces equals 0. So I sub in my forces and set them to 0. And then I need to solve for the terminal velocity squared. And then I take the square root of both sides. So I have an equation for terminal velocity, which includes the Greek letter rho, which is the atmospheric density, which is held constant in this problem. So this idea is going to work best for motion close to the Earth's surface. So that would be sports or perhaps toys. To solve the problem, I'll begin sum of forces equals ma, because that's a good way to solve any problem. So I sub in my forces and I set them equal to ma. I divide through by m, and then I'm going to do a trick. I'm going to take this and set it equal to alpha squared. Notice there's a g in the denominator, so that's why when I sub in the alpha squared, there's a g with the numerator. And I did that just so that I could factor out the g and have a 1 minus form. Now, I know that acceleration is the change in speed per unit time. So that's delta v over delta t. That's the derivative of speed equals acceleration. So I can write a differential equation. Differential equations, they can be difficult to solve. This one is not. I'll multiply across by dt and then divide by everything in the bracket so that I've separated the variables, and then I'll integrate both sides. The interval of integration will go from 0 up to time. The speed will start on 0 since we're falling and go up to v. Now, the left side is easy to take the integral, it's just gt. But what about the right side? You can actually take that integral using partial fractions. But I thought it'd be fun to kind of backdoor the problem. And so we'll pretend it's a rainy day. And we're going to take the derivative of the inverse of the hyperbolic tangent. So there's the identity that we need to take the derivative of. And we're going to use a u substitution. So we set u equal to everything inside. And I'll need u prime, and I'll have to use the quotient rule. So that's why I assign f and g, and I take f prime and g prime. Notice g prime is negative a. So when I use the quotient rule and sub in my stuff, what happens is the ax terms and the negative ax terms cancel, but the a's accumulate, and that's why I get 2a by itself in the numerator for u prime. And I'm ready to go. I can take the derivative of 1/2 natural logarithm of u, which is 1/2 u prime over u. So I sub in u prime, I'll multiply by the inverse, and I have a 1 minus ax on top, and I have a 1 minus ax all squared on bottom. One of those will cancel, and what I'll be left with is a difference of square pattern. So I gather that up, and what I notice is that the derivative of tang ax is like my problem. So by swapping the a's and alphas, I can solve the integral. So now I have an equation involving t and speed. I'll have to solve for speed, but I do that easily by taking the tangent of both sides and dividing by alpha, and I finally have an equation for the speed of a falling object, including air resistance, in terms of time, but it involves alpha. However, I notice that the inverse of alpha squared, square rooted, is the terminal velocity. 1 over alpha equals the terminal velocity. So I can write an equation for speed in terms of time, which involves the terminal velocity. And when I do that, it is really, really nice. The terminal velocity is the asymptote, which the velocity of the falling object never reaches. The straight line is the velocity if the object were falling in a vacuum. It's just v equals gt. But our equation begins falling like a stone, and then the slope begins to decrease. Slope on a speed-time graph is acceleration. As the speed is increasing, the v squared generates more drag, which changes the force equation, which reduces the acceleration. And as the acceleration equals 0, the speed asymptotes to the terminal velocity. So in my next video, I'm going to take the integral of v and get an equation for the distance we fall as a function of time, including air resistance. And wouldn't that be useful? So if you've watched this video and understood it, I would say that you are highly intelligent. So you'll enjoy watching my other videos. Thank you very much, and continue to take care.